nuclear physics, huh? I told you to go through the binding energy curve from the notes. Did you read that section? Yes, that binding energy curve. You have anyone have doubt in that section? Then we can discuss it. No one have doubts, or no one have studied. Yes, Saifullah, Nazia, you went through that section in notes or not?
Not yet, sir.
Okay. Anyways, if you don't want to discuss that topic, then we'll move to the next chapter, that's semiconductor. Semiconductor is a very long chapter, but 70% of semiconductor is deleted from the CPSC syllabus. A very small portion is left. And that too is very theoretical. So that's why I've shared the notes in the group. So the same notebook. So let's start with the semiconductor. So let's first compare between conductors, insulators, and semiconductors on the basis of conductivity. If we talk about conductivity, then the conductivity of the insulator is minimum. Conductivity of semiconductor is maximum. Conductors are maximum, and the conductivity of semiconductor is in between insulator and semiconductor. Similarly, if we talk about resistivity, what is resistivity? It's 1 by conductivity. So if conductivity of insulator is large, that means resistivity of insulator is, sorry, conductivity of insulator is small, so the resistivity of insulator will be large. Then you have resistivity of semiconductor, then you have resistivity of conductors. So the conductivity of conductors is maximum and resistivity of the conductor is minimum. So if we want to compare material on the basis of conductivity and resistivity, which one is a better material, semiconductor or conductors? Aji, what do you think? Which one is a better material? Conductor is a better material or semiconductor is a better material? Because we usually prefer material having high conductivity. So Miraj, what do you think? Which one is a better material, conductor or semiconductor?
The conductor.
Conductor. But if you look at the entire electronic industry, your mobile phone, every chip, the laptops and everything, they are made up of semiconductors, not conductors. So if conductors are better material, and yes, conductors are better material, they have high conductivity, but still the whole electronic industry depends upon semiconductor. There are many reasons. One of the reason is the modification of current. Like in a semiconductor, you can modify current. But in conductors, if you plot V versus I graph of a conductor, then that graph is a straight line. The straight line shows you can't modify current in a conductor, but you can easily modify current in a semiconductor. And for these type of devices, the modification of current is very important. That's why the entire industry is based on semiconductors, not on conductors. Although conductivity wise, its conductivity is less than that of conductor. The next thing is types of semiconductors. Huh? So we have two types of semiconductor materials. One is elemental. Elemental means these are elements. Two examples of elemental semiconductors is silicon and germanium. Then you have compound semiconductor materials. So compound semiconductor materials could be inorganic, it could be organic. Gallium arsenide is an example of inorganic material. Then you have polypyrrole, these are organic materials. We will stick our discussion to elemental semiconductors only. You have to study silicon and germanium. You don't have to study inorganic or organic semiconductor materials. Now, when we talk about elemental semiconductor material, then you can divide it further into two types. It could be intrinsic, it could be extrinsic. We'll see what does intrinsic means. Intrinsic means these are pure semiconductors. Pure semiconductor means they don't have any impurity atom. Extrinsic semiconductor means they are impure. They have impurity atoms. These are impure semiconductors, which are known as extrinsic. Now, these extrinsic can be further divided into two types, N-type and P-type. So we'll stick our discussion up to silicon and germanium only. We will not study inorganic or organic semiconductors. We'll start with intrinsic semiconductor first. Note it down. Just note these values, okay? Only. No need to route these things. I've shared the notes. You can go through the notes. Just note these terms only. These are important terms. Just note down this elemental semiconductors, intrinsic, extrinsic, then just extrinsic are of two type, N type. It's very theoretical. No need to write all derivations. Derivations you can check from notes. I hope you have written it.
1 minute, sir. Yes, sir, done.
Next is energy band in solids. The whole semiconductor physics is based on band theory. So what are bands? Bands are closely spaced energy levels. We studied atoms recently. So if you look at atom have energy levels, n equal to 1 level, n equal to 2 level. These all were energy levels of atom. We studied hydrogen atom. So if you have a single electron, then you have some energy levels. But if you have an atom having multiple electrons, silicon is one example. So if you have a multi-electron atom, each electron will have its energy levels, and these energy levels combine to form bands. So bands are nothing but closely spaced energy levels. So in hydrogen atom, you have single electrons, so you have different energy levels. But if you have an atom having multiple electrons, then those multiple electron system will form bands. You can divide bands into two types. Your bands could be a valence band or it could be a conduction band. Valence band have only valence electrons. They are bounded, and bonded electron does not participate in current. So bonded electron does not participate in current. So in valence electrons in does not participate in current. Only free electrons can contribute in current, not the bonded electron. So the electrons which are in valence band will not contribute to current. This is one more important thing. See, when we say that electrons are in valence band, that simply means electrons are bonded with their respective nucleus. Electrons are in valence shell. Electrons are not free. They cannot contribute in current. The next is conduction band. Conduction band means free electron. Electrons, you make these electrons free. So free electrons means electrons are in conduction band. So when we say electrons are in conduction band in band theory, we mean the electrons are free now, and these free electrons can contribute to current. And there's one more thing. To free electrons, you have to provide some energy. Electrons will get free when they move from valence band to conduction band. To move electrons from valence band to conduction band, you need to provide some energy. And that energy is known as energy band gap. Sorry. This is known as energy band gap. This is also known as forbidden energy gap. So the energy required to transfer electrons from conduction band to valence band to conduction band is known as energy band gap, or you can call it as forbidden energy gap also. So that was about bands. Bands are closely spaced energy levels. You have two types of bands. It's valence band or conduction band. Valence band have valence electrons. Conduction band have free electrons. Electrons of the valence band cannot contribute to current, but electrons of conduction band contribute to current. To transfer electrons from valence band to conduction band, this means you want to free electron. If you want to free some electrons, you have to provide them energy. So the energy required to jump electron from valence band to conduction band is known as energy band gap, or you can call it as forbidden energy gap also. Is it clear? Saifullah,
Yes.
Sakina,
Yes, sir.
any doubt up to here? No doubts. Okay, I have some questions then. Hishma, can electrons of valence band contribute to current?
No.
Why not? Why electrons which are in valence band cannot contribute to current? Nabil?
Sir, because they are bound.
Because they are bonded. They are not free. Only free electrons can contribute to current. Bonded electrons cannot contribute. The next question is distinction between metals, semiconductors, and insulators on the basis of band theory. The difference between metals, conductors, and insulators on the basis of band theory. So let's differentiate between them. How can we differentiate between metals, semiconductors, insulators on the basis of band theory? So we have two types of band, valence band and the conduction band. Free electrons are in conduction band, bonded electrons are in valence band. And the difference between the valence band and the conduction band is known as energy band gap. When we talk about metals, metals means they have free electrons. So what do you think? In metals, conduction band should be empty or it should be filled? Noah. In metals, conduction band should be empty or it should be filled?
So filled.
Filled, because metals means they have free electrons. That's why metals are good conductor of electricity and heat also. So in metals, conduction band is partially filled, valence band is filled, and there is no energy gap between the valence band and conduction band. Means to free electrons, you don't have to provide any energy. There's no energy gap between them. So that's the band diagram for metal. So in metals, conduction band is partially filled. There is no energy band gap. See, conduction band is partially filled. Don't have to provide any energy to free electrons. Free electrons are always there in metals. Or you can show it in this way. This is conduction band. This is valence band. They overlap. So this is the overlapping between the conduction band and the valence band. This is the overlapping. This overlapping shows that there is no energy band gap between the conduction band and valence band. Means you don't have to, zero energy band gap means you don't have to provide any energy to free electrons. That's it. So again, metals, you can explain metals in two ways. First is valence band and conduction band. Valence band is filled, conduction band is partially filled. It means you don't have to provide any energy. That simply means energy band gap is zero, no energy band gap. You can explain metals in one more way. You can say that valence band and conduction band will overlap with each other. So when they overlap, there is no energy band gap. See, this is valence band. Valence band, okay. Sakina bus. Valence band will have just one energy level, it will have multiple energy levels. We just discussed what is band. Sakina bus. Valence band will have just one energy level, it will have multiple energy levels.
Sir, only one energy level.
Sakina? Yes, Sakina. So valence band will have only one energy level or multiple energy levels?
Multiple energy levels.
Multiple energy levels, Sakina. See, this is the definition of bands. Bands are closely spaced energy levels. Fine. So these bands have multiple energy levels. Closely spaced. Okay, after metals, let's discuss insulators. So Saifullah, what do you think? In insulators, conduction band should be filled or it should be empty?
It should be empty, sir.
It should be empty. And what about the energy band gap? That should be small or it should be large?
Large.
As Saifullah said, insulator means they don't have free electrons, means conduction band is absolutely empty. And energy band gap is very large. That's why you can't convert an insulator into a conductor just by heating it. So when you show this in band theory, you show it in this way. This is valence band. This is conduction band. See, valence band, these lines shows that valence band is filled. Conduction band is empty, energy band gap is large. It's greater than 3 electrons. So no free electrons, it's empty, large energy band gap. See, this EV means this valence band have multiple energy levels. The topmost energy level of valence band is EV. Similarly, conduction band will have multiple energy levels. The bottommost energy level of the conduction band is EC. So that's about insulators. Okay, now when we talk about insulators, see, insulators are in between, sorry, now talk about semiconductors. Semiconductors are in between insulators and conductors. In semiconductors, energy band gap is small. It's less than 3 electron volt. Energy band gap is small. It's less than 3 electron volt. Conduction band is empty. But since energy gap is very small, so if you provide some small amount of energy, then electrons can jump from valence band to conduction band. And for silicon crystal, that energy gap is 1.1 electron volt. For germanium crystal, that is 0.72 electron. So if you have a semiconductor, if you look at semiconductor at 0 Kelvin, conduction band is empty. It does not have any free electron. But if you start increasing the temperature and the energy is around 1.1 electron volt, then some electrons can break from their atom or the valence shell, or you can say that electrons will jump from valence band to conduction band at 1.1 electron volt if it's about silicon. But if you have germanium crystal, then electron will jump from valence band to conduction band at an energy of 0.7. So this is valence band and this is conduction. So this is first question that you can get on semiconductor. The first question is differentiate between metals, insulators, conductors on the basis of band theory. Note it down. Miraj, is it clear?
Yes, sir.
It's a very important question. Differentiate between these three types of materials on the basis of band theory. And while drawing band diagram, take care of EV, EC. Mention that this is valence band, this is conduction band. This is valence band, this is conduction. Don't take notes of, don't take screenshot of this section. If I'm asking you to take note of something, that's important. These are the questions that will come in your exams. So don't take notes of definitions, they won't come, but the topics that will come in your exam, you should take note of that. Can I scroll it now? Safullah, written up to here?
Yes, sir.
Hold on. Can I scroll it if you have written? Shagina, Miraj.
Yes,
Shubha?
sir. Done, sir.
And you have to remember this value, like in silicon, it's 1.1 electron volt, germanium, it's 0.72 electron volt. We have to memorize this number. Yeah. Can I scroll it now?
1 minute, sir.
Yes, Avula. Written?
Yes, sir, done.
Now, this is one conceptual question, that why silicon is preferred over germanium, sorry. So there are three answers: that silicon can be worked at high temperature, its melting point is higher than germanium. Silicon have low leakage current, and it's a low cost material. So you can do it from notes only. It's a conceptual question. Then we have intrinsic semiconductor. So these elemental semiconductors can be divided into two categories. It could be intrinsic or it could be extrinsic. When we say intrinsic, that means a pure semiconductor. If it is silicon, it will have silicon only, no impurity atoms. So silicon have four valencies, four electrons in the valence shell. So it will make four bonds to complete its octet. Here in semiconductor physics, each of this line will shows the sharing of one electron. So it's not a covalent bond. One line is showing sharing of one electron. So these two lines will show the sharing of two electrons. So if you want to compare it with covalent bond, then these two lines will represent a single covalent bond. So this simply shows that this silicon is sharing two electrons with the neighboring silicon. Similarly, this silicon is sharing one electron with the neighboring silicon, one with this, one this. The octet is over. So is there any free electron here?
No.
So how it will behave? It will behave like a conductor. It will behave like an insulator. It have no free electrons. So how it will behave, like a conductor or like an insulator?
Insulator.
It's an insulator, right? There's no free electrons. This is at 0 Kelvin. The very low temperature. There's no free electron. But when you raise temperature, let's say at room temperature, at high temperature, what happens is at room temperature, you are providing some energy to the crystal. If that energy is equal to 1.1 electron volt, that energy can break this bond. It can remove this electron from the silicon. So this electron becomes free. This is a free electron now. Now, if this electron becomes free, there is a vacancy of electron, because silicon need 8 electrons to complete its octet. You provide some energy and this electron gets free. So you have vacancy of one electron. And in semiconductor physics, we treat this vacancy of electron as a charged particle, which is known as hole. So here, hole are positively charged particles. We're treating this vacancy as an electron. So these are positively charged particles, which are known as holes. So at low temperature, no free electrons, but at high temperature, this bond will break. Some electrons will get free. So when electron get free, there is one vacancy of one electron. We call that vacancy as hole. Although hole is not a particle, it's just vacancy. But in semiconductor physics, we treat that vacancy as a charge particle. So we have two types of charge particle. One is electron, another is hole. So if one bond breaks, you will have one electron and one hole. If 10 bonds break, then we'll have 10 electrons and 10 holes. How much energy does silicon need to free one electron? Ishma? How much energy this electron will need, this silicon crystal will need to free one electron?
1.1 electron.
1.1 electron. Well, if it is germanium, this will be 0.72 electron. So one electron and one hole. So number of electrons will be equal to number of holes will be equal to the intrinsic concentration. Number of electron means number density. Number density means number of electron per unit volume. Number of electrons per unit volume is number density. And Ni means intrinsic concentration, means number of electrons and number of holes when your material is intrinsic. It does not have any impurity. So any NH is equal to Ni square. So this is intrinsic semiconductor. So if you have intrinsic semiconductor, that means a pure semiconductor. It have no impurity atoms. The number of electrons and number of holes is exactly equal. And if you look at the band diagram, this is the energy band diagram. So this is energy band diagram at 0 Kelvin. All electrons are in this valence band only. See, conduction band is empty because energy gap is 1.1 electron volt at 0 Kelvin. This is 0 Kelvin. At 0 Kelvin, you don't have energy to send these electrons to the conduction band. But when you increase the temperature greater than 0 Kelvin, then some electrons can jump to conduction band. And when electrons jump to conduction band, you have some holes here. So see, 4 electrons jump to the conduction band and you have corresponding 4 holes. This is intrinsic semiconductor. So no need to write everything. Just write this point. Just write down the name, intrinsic semiconductor, which is pure semiconductor. Then after writing this, write down this point, that's it. And then draw the band diagram. So in intrinsic
Sir, are
yes.
sir, are all intrinsic conductors insulators?
At 0 Kelvin, yes. At 0 Kelvin, intrinsic semiconductors are insulators. In fact, all semiconductors are insulators at 0 Kelvin. You don't have free electrons. But when you use them at room temperature, you provide sufficient energy so that electrons can get free. Okay.
Okay, sir.
So in intrinsic, this point is important. Any NH is equal to Ni. This equation is important. Any NH is equal to Ni square. You should remember these things. What are holes exactly, Noah?
So vacancy of electrons.
Vacancy of electrons. And Miraj, how much energy do we need to free an electron from a silicon crystal? Mehraj Rahman, how much energy you need to free electron in a spherical crystal?
Sir, I don't know.
I just wrote the energy band gap for silicon. Just turn your pages and check. What is the energy band gap for silicon, Mehraj? You're not taking notes, huh? It's 1.1 electron volt. So for silicon, you need 1.1 electron volt to free electrons. What about germanium, Mehraj?
Sir, 2 electron volts.
0.72. 0.7. Miraj, note down the sections which I'm asking you to take notes. Take notes of this section, take note of this section. I hope you must have written up to it. Then draw the band diagram. So Miraj,
Sir,
this
1
is
minute, sir.
just write down these 2 points only. Any NH is equal to Ni, any NH is equal to Ni square. Jasola, written.
Yes, sir.
Sure. So this is energy band diagram. This is energy band diagram. So 1.1 electron volt for silicon, 0.72 electron volt for germanium. This is the band gap. At 0 Kelvin, conduction band is empty. So Miraj, it's behaving like a conductor or it's behaving like an insulator? This semiconductor, just look at this band diagram and tell me it's like it's a conductor or it's insulator right now.
So it's an insulator.
Why?
Because sir, the conduction band is empty. It does
Very
not
good.
have any.
Conduction band is empty, so it's behave like insulator. But here you have some electrons in the conduction band, so it will have some. Draw these two band diagrams. So you should know the difference between the energy band diagram at 0 Kelvin and at room temperature or high temperature. Can I scroll it now?
Sir, um,
Mhm.
sir, for the second energy band, is it T70 Kelvin or
T
770 Kelvin?
sorry, T is greater than 0. Sorry, T is greater than 0. Okay. Now, we cannot use intrinsic semiconductors for any commercial purpose. The reason is there are two problems with the intrinsic semiconductors. One is they have very low concentration of charge carriers. Second, the energy band gap is very large. 1.1 is small as compared to insulators, but still it's large. You can't make any device which you can use commercially using these type of semiconductors. So this is again a question. Important question. What are the limitations of intrinsic semiconductors? There are two limitations. Energy band gap is large. Concentration of charge carrier is small. So again, no need to write it. Do it from notes. Okay, then this is doping. So intrinsic semiconductors have issues. To resolve those issues, we do doping. Doping means adding impurity atoms in an intrinsic semiconductors. We don't add any impurity atom. We add only those impurity atoms which are desired impurity atoms. So this process of adding desired impurity atoms into the intrinsic semiconductor is known as doping. The process is doping and the impurity atoms are known as dopants. So due to doping, this conductivity of the semiconductor will increase. So extrinsic semiconductors, when you doped an intrinsic semiconductor, the semiconductor that you obtained is known as extrinsic semiconductor. So we can make extrinsic semiconductors in two ways. We can add some type of impurity atoms which can increase the number of electrons. They are known as N-type semiconductors. If you increase the number of electrons, then the extrinsic semiconductor is N-type. If you increase the number of protons, oh sorry, not protons, the number of holes, then we call extrinsic semiconductors as P-type. So N-type. N-type means you're adding pentavalent impurity atoms. Means arsenic, phosphorus, this group 15 elements. Electrons are majority charge carriers and holes are in minority charge carriers. So you will have more number of electrons than holes. Pentavalent means it will have 5 electrons in the valence shell. So this is the silicon crystal. In silicon crystal, you put a phosphorus atom. This phosphorus have 4 electrons in the valence shell and there is one extra electron. This is not bounded with any silicon. See, these 4 electrons will make bonds with the silicon. It will complete its octet. This fifth electron, this is fifth unbounded electron. This will not make any bond. So, Nabil, if I compare this electron, which is bonded with the silicon, and this fifth electron of phosphorus, which one is weakly bounded?
The fifth electron.
The fifth electron. What do you call this electron in chemistry? Lone pair? No. Free radical? The electron which does not take part in bond formation. What do you call that electron?
Lone
Free
pair,
radical.
sir.
Lone.
Lone pair.
So this is that free. This electron is not free, but it's not taking part in any bond formation. So it's weakly bonded. Now, if you want to free this electron, you have to provide a very small energy, like 0.01 electron volt for germanium and 0.05 electron volt for silicon. If this phosphorus is in germanium crystal, then to free this lone pair, this electron, you need just energy of 0.01 electron volt. See, the band gap decreased drastically. Earlier it was 1.1. You need 1.1 of energy to break silicon-silicon bond. But to free this electron, you need 0.01 electron volt and 0.05 electron volt for silicon. So each phosphorus atom will contribute 1 electron. So if you're adding 1 mole of phosphorus atom, that means you're adding 10 raised power 23 atoms of phosphorus. That means you are adding 10 raised to the power 23 electrons. So each phosphorus atom will give 1 electron and no holes. You will get holes when silicon-silicon bond will break. When electrons comes from the silicon-silicon bond, then only you will have holes. Here, there's no hole, only electrons. But along with this phosphorus, there is one more source of electron, that is silicon-silicon bond. At room temperature, you have sufficient energy to break these bonds also. So when these bonds break, let's say by energy of 1.1 electron volt, you will have 1 electron and 1 hole. So Hishma, which one is in majority in these type of charge carriers, electrons or holes?
Electron.
Which two process contribute electrons here? Can you name both the process which contributes electrons here? One is this lone pair of phosphorus and another one is this thermally generated silicon-silicon. So these are the two processes from which you get electrons. One is from the phosphorus, another is from silicon-silicon. And since phosphorus give electrons, that's why we call phosphorus as donors also. So due to thermal energy, electrons and holes are generated, and this crystal is absolutely neutral. See, phosphorus is giving 1 electron, but it's getting some positive charge also. So there is no net charge on the extrinsic semiconductor. It's perfectly neutral. Next, if you want to draw energy band diagram, see there is one new thing. Electrons comes from the valence band when they are coming from silicon-silicon. When electrons are getting free, that means they are going to covalent bond. So if I talk about this electron, let's talk about this particular electron. Jasola, is this electron coming from the silicon-silicon band? Silicon-silicon bond?
No, sir.
Okay. Anshika, sorry. Is this electron coming from the valence band? Anshika, is this electron coming from the valence band? Nazia, is this electron coming from the valence band? Open question.
Sir,
Why not? Why this electron is not coming from the valence band?
because the conduction is due to the conduction band.
No. I'm asking, this electron is getting free. It's going to conduction band. But I'm asking, is it coming from the valence band? See, it's not coming from the valence band. The reason is, if you say that electron is coming from the valence band, that means electron is coming from silicon-silicon bond. Valence electrons here means silicon-silicon. So if electrons are coming from silicon-silicon bond, then in band theory, we say that electrons is coming from valence band. If electrons are getting free, that means that we say in band theory, we say that electrons are coming in conduction band. So let's ask this question with Sakina again. Sakina, is this electron, this silicon-silicon bond electron, is it coming from the valence band?
Yes, sir.
And is this electron going to conduction band? This one? Yes, Sakina. Is this electron going to conduction band? Yes, it's going. See, again, I'm repeating. If electron is coming from silicon-silicon bond, then in band theory, we say that electron is coming from the valence band. If electron is getting free, then in band theory, we say that electron is coming to the conduction. Is it clear? So this electron is getting free. It's getting free. It's going to conduction band. Nabil, is it coming from the valence band? Nabil Ahmed,
Yes, sir.
listen again. I'm asking, is this electron coming from the valence band? Just check. Is this electron coming from silicon-silicon bond?
No, sir.
If not coming from silicon-silicon bond, that means not coming from valence band. Coming from valence band means it's coming from silicon-silicon. So this electron is not coming from valence band, but it's going to conduction band. That means you have some new energy levels. So what happens in N-type semiconductors, some new donor energy levels get created just below the conduction band. So electrons are not coming from valence band to conduction band. Electrons are coming from this donor energy level to conduction. And they need comparatively small energy, 0.01 electron volt for silicon and 0.05, not 0.5, yeah, 0.05 electron volt if you are taking a silicon crystal. Here also, this relation NE/NH is equal to Ni square is valid. This Ne here is very, very greater than NH. Number density of electrons is very, very greater than number density of holes. Or you can say the number density of electrons is almost equal to the donor atoms. Donor atoms means this phosphorus atom. The majority of electrons here are coming from the phosphorus atom. There are few electrons which are coming due to the thermally generated electrons, which are coming from silicon-silicon bond also. But the majority is coming from the donor atom. Is it clear the creation of donor energy levels? Noha, Naziha, Miraj, Arpit.
Yes, sir.
Yes, sir.
This donor energy level is very, very important. Now do it. Don't draw this diagram. Just write down these first 2 points. Note it down. Just note down these 2 points. Pentavalent impurity atoms you add, electrons are majority charge carriers, holes are in minority charge carriers. Can I scroll if you have written these 3 points?
Yes, sir.
No need to draw this diagram, it will take much time. No need to write it, not to write it. Just draw the energy band diagram and these points. Right, main points only. The rest of the detail you can check from the notes already shared. Draw this band diagram. This is very important. So Nabil, NE is exactly equal to ND. Nabil.
Sir.
Yes, Nabil. NE and
No,
ND
sir.
are, so
Some are
NE.
because of silicon also, some electrons.
So what you say, if I write to be exact, NE is equal to ND, N is greater than ND, or N is less than ND?
Ne is greater than Nd.
Good. Because electrons will come from phosphorus as well as from the thermally generated. Right now we are ignoring electrons which are thermally generated. Can I scroll it if you have written?
1 minute, sir.
Arpit, are you getting it? You came late.
Yes, sir, little part.
So very small chapters. Okay.
Yes, sir, done.
Okay, so quickly, can you point out some basic features of N-type semiconductors? Okay, Arpit, let's start from you. Just tell me one point about the N-type semiconductors, about the type of impurity you can choose. Arpit, what type of impurity atoms we add in N-type semiconductors? Krishma? What type of impurity atom we add in N-type? Raj? यार ये बहुत गुस्सा आता है तुम लोग गायब हो जाते
Sir, phosphorus.
phosphorus pentavalent impurity atom, right? In N-type we add pentavalent impurity atoms. So which one is majority and minority charge carrier, Saifullah, in N-type?
And sir, electrons are in majority, whereas holes are in minority.
Okay. So is there any change in the energy level diagram, band diagram?
Yes.
Yes. Nazia, what's the difference in band diagram of N-type semiconductors?
There is the additional donor energy level
And what's the cause of this donor energy level?
due to the unpaired electrons of phosphorus.
Yeah, that's
And
phosphorus, right? And this is the expression, Ne NH is Ni square. What is Ni, by the way? We discussed Ni in intrinsic semiconductors. Sakina Abbas, what is Ni? We discussed this term in intrinsic semiconductors. Raj, what is Ni? We discussed this term in intrinsic semiconductors. Yes, Miraj. What is Ni? Hishma, what is Ni here?
Intrinsic concentration.
Intrinsic intrinsic concentration. This is the concentration when your semiconductor was intrinsic. It was the concentration of charge carriers before adding all impurities. So that was about the N-type. Next, let's do P-type. So instead of N-type, if you're adding, instead of pentavalent, if you're adding trivalent impurity. Trivalent means atoms which have 3 electrons in the valence shell only. They are known as acceptor atoms. This boron, aluminum, gallium, this group, this is trivalent. In P-type, holes will be the majority charge carriers, and just like N-type, it would be neutral. So see how we get extra holes here. Now, when say you have aluminum, this aluminum have 3 electrons in the valence shell. So there is a possibility that this hole can jump from the silicon-silicon bond to here. There's a possibility that this hole can jump from here. So when this electron jump from silicon-silicon bond to here, then there is a vacancy of electron which is known as hole. And if you can see, there is no free electron. See, I'm repeating again. This is aluminum. This have 3 electrons in the valence shell. It have 1 electron less to complete its octet. So what it will do, it will take 1 electron from the silicon-silicon bond. When this electron from silicon-silicon bond shift here, this vacancy of electron, and this vacancy of electron is known as holes. So this is the vacancy which is known as holes. So as you add 1 aluminum atom, you get 1 hole, no electron. So if you add 1 mole aluminum atom, you will get 1 mole holes, 10 raised power 23 holes. So the holes are coming due to this acceptor atom. We are calling it acceptor because it's accepting 1 electron from the silicon-silicon bond. And it will become negatively charged. Since it's accepting 1 electron, it becomes negatively charged. And along with this aluminum, you will have electrons which are thermally generated also. Some bonds will break. Now, silicon-silicon bonds will break. And due to the breaking of this bond, you will have free electrons also. And when you have electrons, you have holes. So when silicon-silicon bond break, 1 electron and 1 hole will generate. But this sector atom, this aluminum atom will contribute 1 electron. Sorry, it will contribute hole. So this is it. So this is P-type semiconductor. You have holes in majority. And let's predict the change in band diagram here. See here, the electrons are come from silicon-silicon bond. Nazia, sorry. This electron is coming from silicon-silicon bond, right? So can I say that this electron is coming from the valence band? Nazia.
Yes, sir.
Okay. Nabil, can I say that this electron is going to the conduction band?
Yes, sir.
Yes, sir. Saifullah. Can I say that this electron is going to the conduction band? This electron, which is jumping from this silicon-silicon bond to this aluminum.
No, sir. I don't
No,
know.
it's not going to conduction band. It's not getting free. It will come to conduction band if it becomes free. No, it's not becoming free. It's jumping from here to the aluminum. So it's not getting free. So it's not going to conduction band. So you have 1 electron which is coming from silicon-silicon bond. That means you have an electron which is coming from the valence band. But it's not getting free. It's not going to conduction band. That means you have new energy levels. So here you have acceptor energy levels just above the valence band. So the electrons jump from here to here. It's not getting free. It's just jumping from valence band to the acceptor energy levels. So that's the difference. And energy difference is same, just like the silicon 0.05 for silicon and 0.01 for silicon. This equation is same. Ne NH is Ni square. The difference is NH is very, very greater than Ne. And NH is almost equal to Na, equal to the acceptor atoms. So if you're adding 1 mole aluminum, then you will say you will have 1 mole of holes. But you know you will have holes slightly more than 1 mole because some holes are coming from silicon-silicon bond also. So that's P-type. Note down these points. This band diagram is very small, very important. So in P-type, just above the valence band, you have some acceptor energy levels. And the acceptor energy levels are due to the aluminum atom.
So can you explain that part again, sir, when the valence electron is coming to the conduction bond, sir?
Yes, so till others are writing explaining. See, We have two types of bands basically. You missed the starting portion of the class now, the band theory. We have two types of band. One is valence band, another is conduction band. Valence band means band which have valence electrons. So if electrons are in the valence shell of the silicon, we say that electrons are in valence band. Conduction band means electrons are free. So if you have free electrons, that means those electrons are in conduction band. Now here, the electrons are jumping from silicon-silicon bond, right, Arpit?
Yes, sir.
So electrons are coming from the valence band. But electrons are jumping to the aluminum. They're not getting free. If electron gets free, then we say that electron is going to the conduction band. It's not getting free. It's just jumping to the aluminum. So we say that yes, electrons comes from the silicon-silicon bond. So in band theory, electrons comes from the valence band. But since it's not getting free, so it's not going to conduction band. You are some new energy levels are creating. No need to draw this. So the physical reality is electrons are in valence shell. To explain that thing in band theory, we draw valence band. We say electrons are in valence band. When electrons gets free, then we say that those electrons goes to conduction. Arpit.
Yes, sir. Clear.
Let's draw this band diagram. This is important. These are important questions. Draw the band diagram for N-type and P-type semiconductor and explain from where does you get energy, acceptor energy levels. Yes, Arpit, we can discuss it. Or Arpit, we can discuss it over a call also. We can have a call at the end of class.
Yes, yes, sir.
That would be better. So let's do some questions on this extrinsic semiconductors, and then we'll study what is p-n junction and how we can make a p-n junction. So everyone have written up to here. This NH is equal to Na, acceptor atom.
Yes, sir.
1 minute, sir. Yes, sir, done.
Let's start with this thing. Note down this question. Written this question. So everyone have written the question. Huh? Let's solve it together. See, this is the formula of this. Second, Abbas, what does ppm means? Must have did this thing in electronics. Sorry, solutions in chemistry.
So parts.
Parts per meter. Huh? So you have just 1 second. So a pure silicon crystal has 5 into 10 raised to the power 8 atoms per meter cube. It is doped by 1 ppm concentration of pentavalent arsenic. So the number of arsenic atoms, numbers of arsenic atoms is equal to, see, this is the number of silicon and you're adding arsenic as ppm. So ppm means take the number of silicon atoms and divide it by 1 million. ppm means part per million. We're using solution chemistry. So 10 raised power 6. So it comes out to be 5 into 10 raised to the power 28 per meter cube. Arsenic is donor. So you have number density of donor atoms. Huh? Number density of, sorry, exactly. Number density of donor atom is 5 into 10 raised power 20 per meter cube. Now this number density of donor atom is exactly equal to the number density of electrons. Free electrons. The number density of electrons is this 5 into 10 raised power 22 meter cube only. Now you have intrinsic concentration also, which is 1.5 into 10 raised to the power 16 per meter cube. You need NH only. For NH, we can use NeNH is equal to Ni square. So you can write that NH is equal to Ni square by Ne. Complete these calculations and write your answer in chat room. I need the value, the number of holes. Do it. Answers, please write your answers in chat. Need the value of it. Okay, Noah, good. I got one answer from Noah only. Okay, Nabil, good. Okay, Sakina, correct answer. What about the rest? Ishma. Okay, Arpit, good. Ishma, good. Second Abbas. Just have to complete the calculation. That's it. Ni is, how much is Ni? It's 1.5 into 10 raised power 16. It's given here. Huh? Right, Saifullah? This square. Divided by Ne, which is this number. 5 into 10 raised power 22. So you can write this as 1.5 square is 2.25, right? into 10 raised to the power 32 divided by 5 into 10 raised power 22. So when you cancel this, 5, 4, 5, 5, 5. So this is 4.5 into 10 raised to the power 10 per meter.
So it is 0.45.
0.45. Yes, sorry, 0.4. Zero point 0.45. Noted. Haji, can I scroll it now? Raj, clear?
Yes, sir.
Sakin Abbas, any doubt in calculation?
No, sir.
So let's move on to next. Now, these are the terms that we have taken from current electricity only. In semiconductors, the current is due to electrons as well as holes. So in semiconductor, we used to write NEAVD. So this is VD of electron, where VD was drift velocity. So I'm writing these expressions from the current electricity itself, chapter number 3. So this is electrons and this is holes. So you can write the expression of current as current due to electrons plus current due to holes. Similarly, in conductivity, we can write it's E, Ne mu E plus NH mu H. N is number density, mu is mobility. Mobility of electrons is greater than the mobility of holes. Does anyone remember the formula for mobility that we did in current electricity? Mobility. Mobility is drift velocity per unit electric field is VD by. Note it down. You should know these relations. Usually no one asks these questions in semiconductors, but these questions can be asked from current electricity. This is current electricity. Instead of electron, you're having two particles only, electrons and holes. Note it down. It's not in NCRT, so there are very small chances of getting this question from semiconductors, but this is in current electricity. You can expect this question in current electricity. Haji, can I scroll it now?
1 minute, sir. Done, sir.
The next is p-n junction. See, we use semiconductors so that we can control current. We can't control current in p-type material. We can't control current in n-type material, but we can control current in p-n junction. So the element from which we make semiconductor devices is not p-type, it's not n-type, it's p-n junction. So we make p-n junction, then using this p-n junction, we make further devices. So how we make p-n junction? See, so for p-n junction, you have to put a p-type and an n-type material nearby. So you have to place a p-type material in contact with an n-type material. And these contacts should be that of atomic level so that they can exchange their electrons and holes. So what we do is we take for practically what we do, we take a intrinsic plate, intrinsic semiconductor. We put n-type, pentavalent impurity at one place. So when you add pentavalent impurity, what type of semiconductor you get, n-type or p-type? Safula? If we add
P-type.
pentavalent,
For pentavalent,
what type of semiconductor we get?
N-type.
N-type. Then we add trivalent impurity. Then what type of semiconductor will get? P-type semiconductor, right? When you add trivalent, you get P-type. When you add pentavalent, you get N-type. So you take a plate, intrinsic plate, then you add a P-type, pentavalent impurity at one side and trivalent impurity at one side. When you add trivalent impurity, you get P-type, and when you add pentavalent impurity, you get N-type. Next, Sakin Abbas, what are majority charge carriers in P-type? We'll explain entire PN junction on this figure only. Naziha Abbas, what are the majority and minority charge carriers in P-type semiconductor? You can check from your notes also. Na? You have written the majority and minority charge carriers there.
The holes.
Yes, holes are majority charge carriers in P-type and electrons are minority charge carriers. And if you take N-type, then in N-type, electrons are majority charge carriers and holes are minority charge carriers. Now see, what happened when you put P-type and N-type in contact? The diffusion happens. What does diffusion mean? The flow of molecules from high concentration to low concentration, just like a bottle of perfume. If you open a bottle of perfume in a room, then the molecules of perfume will move from bottle to room, because in bottle their concentration is high, and in room the concentration of molecules of perfume is small. So this is exactly what happens when you put a p-type material in contact with an n-type material. The diffusion starts. Diffusion start means the flow of majority charge carriers. Means holes will start moving from p to n and electrons will start moving from n to p. This flow of majority charge carriers across the junction is known as diffusion. Flow of majority charge carriers. Holes from p to n and electrons from n to p. Now, when a hole, what type of material is p-type? P-type is charge or it's neutral? If I say p-type material, is it charge material or neutral material?
Neutral.
It's neutral. Neutral means it have equal amount of negative and positive charge. That's why then only it could be neutral. Huh? If you are taking some holes from p-type material, you are transferring positive charge. So what type of charge will come on the p-type if you are taking some positive charge outside? What type of charge will
Negative
come on
charge.
the negative charge? So due to the diffusion, due to the motion of holes from P to N, see, you can see here, the negative charge starts building here, 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 here. This negative charge due to motion of these holes. And this negative charge is on ions. This negative charge is not on any electron or proton we are talking about. We are talking about this negative charge on ions. And ions are immobile. They can't move. Immovable. They're not charge carriers. Similarly, when electrons come from N to P, you get vacancy of electrons, means there are less negative charge. So we'll have positively charged ions. Again, these are ions. These are ions. They're not charge carriers. Immobile ions. They can't move. So due to diffusion, on P side, you have negatively charged ions, and on N side, you have positively charged ions. So this is what we call diffusion. Is it clear? Diffusion, up to diffusion, is it clear for everyone? Noha, Sakina Bas, Miraj, Arpit.
Yes, sir.
Yes, sir.
Arpit, is diffusion clear?
So can you repeat it?
Arpit, what are majority charge carriers in P-type?
So I have not listened to it, sir. I had gone to fetch my charger.
I won't repeat that. See, in P-type, holes are majority charge carriers and electrons are minority charge carriers.
Yes, sir. So you were on the point when you told about perfume, sir. I had listened till there.
Sure, okay, I'm saying that diffusion means flow of particles from high concentration to low concentration. So I was giving the example of perfume bottle. Like when you open the bottle of perfume, the molecules of perfume moves from the bottle to the room. They are moving from a system, a region of high concentration to a region of low concentration. Similarly, when you put a P-type material in contact with an N-type material, in P-type material, you have holes which are in majority. In N-type, you have electrons which are in majority. So the diffusion starts, means hole starts moving from P to N and electron starts moving from N to. Due to the diffusion of holes and electrons, you will have ions. When holes move from P to N, you have negatively charged ions. When electrons move from N to P, you have positively charged ions. These are ions, they are immobile, they can't carry current.
Yes, sir.
Clear up to here, huh?
Yes, sir. Clear.
Now, these ions will start a new story. So what these ions will do, these ions will generate some field, right? You have a positive charge and a negative charge. So we'll have field from positive to negative charge. This is the field. So these ions will generate a field and see what this field can do. So if you have an electric field and you have a positive charge, this electric field will push this positive charge in the direction of field. And if you have a negative charge, field will push this charge in a direction opposite to that of field. This is what the field can do. It can push a positive charge in the direction of field. It will push the negative charge in a direction opposite to that of field. So this is what happens exactly here. This is the field. Huh? This field will push electrons in a direction opposite to that of field. Means this field will push electrons to the N side. So the electrons which were trying to move to the P side due to diffusion will experience a force due to this electric field towards N. So what do you think, Nabil? This field will help these electrons to cross over the junction? It will oppose its motion.
Will oppose the motion.
It will oppose its motion. So this field will resist the motion of electrons. Similarly, this field will exert some force on this positive charge in the direction of field. This field will resist this positive charge, resist the motion of the positive charge across the junction. See, it's a very simple physics. This is field, this is negative charge. Field exert force on negative charge in the direction opposite to that of field. So field is to the left, that force will be to the right. So this field will oppose the motion of negative charge. This field will oppose the motion of positive charge across the junction. So this field is opposing diffusion. Due to this field, you will have a potential difference, which is known as barrier potential. We call this as barrier because of the field. The field is acting as a barrier for the motion of charge carriers across the junction. Is this clear? The role of field?
Yes,
Miraj,
sir.
Arpit? Miraj left. Nabil? Noha?
Yes, sir.
Yes,
Role
sir.
of the role of field is clear. So this field is opposing the flow of majority charge. This field starts error kahani. What this field will do, this will oppose the motion of this majority charge carriers, but it will start favoring the motion of minority charge carriers. In fact, it will start the motion of minority charge carriers. Before this field, minority charge carriers cannot cross because diffusion happens. occurs only in majority charge carriers, not in minority charge carriers. But what this field will do, this field will pull this hole from N to P, because field will exert a force on positive charge in the direction of field. So this field will pull this hole and will transfer this to across the junction to here. Similarly, this field will pull this electron from the P side to the N side. So this field will promote the flow of minority charge carriers across the junction. And this flow of minority charge carriers is known as drift. This flow of minority charge carriers means electrons will jump from P to N and holes will jump from N to P. Minority charge carriers will jump. This is known as drift. And this is the electric field which starts this drift. If you don't have electric field, you won't have drift. These minority charge carriers cannot jump on their own. They need some external push, which is provided by the electric field. Then a time reach when your system comes in equilibrium. In equilibrium, drift is equal to diffusion. That means there is no net flow of charge carriers. Nothing is flowing across the junction. The system is in equilibrium. Now, write the heading PN junction only. No need to write this definition. You have these notes with you. Now just draw this diagram. This diagram is very, very important. Draw this diagram. Then you will write all definitions. What is drift? What is diffusion and all. Let's draw the diagram.
Excuse me, sir.
Yes.
Sir, initially the holes are at rest.
Initially, the holes are in P type, P side or in N side?
N side.
Yes, initially they were at rest. They can't move. Because diffusion occurs in this in uh, things which have high concentration. Okay. Diffusion occurs in only those particles which are in majority, which have high concentration. Can I scroll if you have written? Safula?
1 minute, sir.
So, one second.
Done, sir.
Note down these terms: diffusion, carrier potential, drift. Yes, written everyone?
1 minute, sir.
Yes, written.
Yes, sir.
So we'll stop here. So just one more class I need to finish semiconductor. The next class will finish this thing. So major portion is over. Just diode is remaining. Diode and this rectifier.